In this video, we're going to talk about the math in the Unit 1 of this chemistry course. So in that unit, we had sig figs, we had dimensional analysis, we had accuracy versus precision, we had percent error, and then we had general factor label method dimensional analysis. So for sig figs, there's a couple rules to follow. Anything that's not a zero counts as being significant. And zeros count sometimes. There's a couple rules to follow. There's two conditions under which they count. Kind of three. One, if they're in between two significant figures, they count. Or they have to be after a sig fig and after a decimal, or immediately preceding a decimal. So those are your three rules. So if we look at this first one, only that zero would count as well as the 2 and the 3. So this first number would only have 3 sig figs. The second one, these 3 would count. And the second one, all 5 of those would count as significant. This one falls between 2 sig figs. This one falls after a non-zero and after a decimal, or after a sig fig and after a decimal. This one falls immediately preceding a decimal. So those all count, and you would have 5 sig figs present there. Now when we're using sig figs to do multiplication or division, all we have to do is look at the number of sig figs in each of the terms. So in this case we have 2 sig figs, in this case we have 3 sig figs, and therefore our answer can only have 2. So we would get 60 point, and that's how we would represent this number with 2 sig figs. You could also represent it as 6.0 times 10 to the first. Then when you're adding or subtracting, all you have to do is line the numbers up, and the furthest place they have to the right in common is what you report your answer to. So in this case, this goes to the 10th place, even though this gives you detail to the 100th. What you would have to do with this is determine whether or not it rounds that one up or leave it what it is. So in this case, that's going to round up and become 1. So that would give you an answer of 4.0. When we're looking at data sets and determining whether they're accurate or precise, accuracy essentially means how close to the correct answer you are, or the true value, and precision has to do with how consistent of a grouping you have. So this first data set, if you look at it, this is a very tight grouping, so that would definitely be precise. And since the true value is very close to that, we would say it's a very accurate data set. The second data set gives you an average that would be very close to the true value. So you can say it's accurate, which I disagree with, but you can say that, and then it has virtually no precision. The last data set is very precise, but it gives you an answer that's not close to your true value. So that would be precise, but it would not be accurate. So those are the possibilities you could have. When you're looking at stuff and seeing how close it is to the true answer, we use percent error to represent that, which is really just what you're off by, or the true value minus the experimental value, over what you should have got, which is the true value, times 100. And then we did density calculations, and density is just the mass of the material, or the quantity of matter, over the space in which it's occupying. So one way we measured density was by looking through water displacement, where you have a sample where you know its mass. If it's an irregular shaped object, this is a good way to do it. And then you have an initial volume in a container. When you put the object in, obviously the container is the water level will go up. The difference in the water levels would give you the volume. So if you're calculating the density here, if it's a 3.6 gram object, you would divide that by the volume of 2.2 mils to get a density of 1.6 grams per mil. And then we did some other dimensional analysis. If you're converting, say, for example, 25 cubic meters to cubic centimeters, you can't just do a one-step conversion there and say there's 100 centimeters in a meter. You have to do that 3 times because it's a cubed function. So after the first step, you would have really just canceled that to meters squared. So if you only did it once, you'd have meters squared times centimeters as your units, not what you want. So you have to do it out 3 times, and then you would get yourself all the way to centimeters cubed. Now this is a way of representing this number, but most of the times you wouldn't consider that very convenient. Converting that to scientific notation, all you do is figure out how many places you have to move the decimal. So if your number goes from big to small, that means you're going to have a positive exponent. So it goes from small to big. So 2.5 times 10 to the 7th is another way you could represent that value. So this is the math from Unit 1, and hopefully that was a good overview for you.